Everyone can hear me? Good? All right. So, let's talk about old stuff. As you said, my name is Larry Garfield, or Krill. If you want to make fun of me on Twitter during the session, that's where you do so. I highly encourage it. I'm the Director of Runtimes, Engines, Integrations, and Services for platform.sh. Yes, the acronym was deliberate. Before that, I spent a little over 10 years as a Drupal consultant with Palantir.net in Chicago. A couple of other Palantir and former Palantir people in the room as well. Hi, folks. Drupal 8 Web Services lead. And I do implement the huggable interface, so if you do as well, let me know. This is a computer. It's a very old computer. Specifically, it's the IBM System 360 Model 20. The IBM System 360 was the first complete range of computers, compatible computers. It was announced in, 1964, and was the first architecture for computers where the same software could run on more than one piece of hardware. This was a phenomenal improvement, a phenomenal innovation. There were a series of different IBM 360 computers, and you could run software on anything from this small one, the Model 20, up through model huge number. It was, of course, like any technology project, announced in 1964, but didn't actually ship until 2 years later, because computers. But because it had this broad target of different systems, it also was one of the first systems to make a distinction between architecture and implementation. The idea that there was an architecture and a design independent of a particular implementation was a new concept. And this was important to allow it to run on a variety of different types of hardware. For example, it could use tape spindles, which were the standard at the time, or this weird newfangled thing called a spinning magnetic disk. I think that might hold a megabyte. This is a very influential system historically. Its legacy is still with us today. For example, the idea of a byte being 8 bits wide came from System 360. Before that, every system had a different definition of what a byte was. This was huge, in fact, because the most common before that was 6 bits, not 8. And using 8 bits gave you enough possible characters to include lowercase letters. This is a phenomenal improvement over earlier systems, where it didn't have enough bits for multiple cases of character. They all used uppercase because science says using all lowercase is better than all uppercase, but the CEO of IBM wouldn't let their company name be shown in lowercase, so they had to use uppercase before that. So they expanded it to 8 bits. The idea of addressing memory by bytes rather than as individual bits is System 360. We take these things for granted today, but these were all innovations in System 360. And of course, the ABCDIC character encoding standard, which no one uses anymore because ASCII won that one. So, can't take everything. But it lives on today as the IBM Z series. This is IBM's high-end mainframe line. Software written for the 360, in some cases, will still run on the Z series. 50-year-old software will still run without recompilation. Cool, huh? And yes, it also runs PHP. I know the guy who maintains the PHP port for it. There's a large development team that built this system, hardware and software. The lead architect was a man named Gene Amdahl. The lead manager for it was a man named Fred Brooks. We're mostly going to talk about Fred here. Brooks, among other things, is the one who coined the term computer architecture. He was the first one to use that phrase. After the project was over and the system shipped, they went on to their other companies and other jobs and eventually ended up in academia, like you do. Brooks, however, went on to write a book in 1975 called The Mythical Man-month. These are the lessons learned from his experience managing the System 360 project, both the good and bad, as well as his later experience in other projects and academic study at the time of how one manages large software projects. In 1986, he released an essay called No Silver Bullet, we'll talk about later, and in 95, released the anniversary edition, which is what I've got here, Looking back on 20 years later, is this stuff still true? Did he get it right? And in his analysis, with a couple of extra chapters, yeah, most of it, not everything, most of it. Knowledge about software management and software technology that lasts for 20 years. That's pretty impressive these days. Well, it's been another 20 years. Still true? What I'd like to do today is look back at some of the things that Brooks goes over in the book and see if 20 years later, 40 years later, they still hold true. Now, I'm going to go over this in a completely different order than Brooks does. I'm going to cover less than half of what's covered in the book. Short version. No one should be allowed to manage a software project without reading this book. Go buy it. It's available on your favorite online reseller or bookseller. No, I don't get a commission for it. I just think you need to read it. So we're going to just go over a couple of points. Let's start with the eponymous Brooks Law, which he'd been using before the book was published, so you could use the name for it. Adding people to a late software project makes it later. Who's familiar with this phrase? A couple of people? A couple of more people are chuckling? Yeah. Why? Why did he make this claim? Well, communication is hard. Also, communication does not scale linearly with the number of people. If you have 2 people on a project, you have one pipeline of communication, one channel. If you have 3 people on a project, you have 3. There's 4 people on a project, you have 6. It's not quite exponential, it's combinatoric. But there's even a formula for the number of communication channels you have to keep track of, depending on the number of people that are involved. And this goes up quickly, and communication takes time. If you need to keep track of 12 other people's work, or talk to 12 other people about something, that's going to slow you down. Even if everyone is being as efficient as possible, it's still going to slow you down. Tasks are also not parallelizable. Not all tasks can be done at the same time by different people. To take an extreme example, I hired you because this will take 300 man days to complete. So I hired 300 people, which will be done this afternoon, right? Yeah, no, that doesn't actually work that way. Resources are limited. You only have so many printers that you can deal with. You only have so many computers. You only have so many different parts of the system. Different people have different skill levels. Some people are just not going to be good working on the front end. Others not going to be good working on the database. And some tasks will block others. I can't build this piece until this other piece is written that it depends on. I may be able to mock something out, sort of, but there's still things I can't build until this other part is done. This is true even for unskilled tasks. A couple of years ago, I helped some friends move from Chicago to New York. Why they're moving from Chicago to New York, I have no idea, but hey. And so we were packing up their apartment, and we had like 8 people. They had 100 boxes. So if we had 100 people, it would have been a really quick job, right? Except we only had 1 elevator, we only had 3 dollies, we only had 1 truck. Not everyone knew which boxes were fragile. Some boxes required 3 people to lift because they were heavy. You cannot parallelize most tasks indefinitely. People and months are interchangeable commodities only when you can partition a task with no communication. If you have to talk to another person at all, then these tasks are not completely parallelizable. There is some dependency there that is going to slow down your progress because you have to talk to another person. Additionally, adding people to a project after it starts has a cost. How long will this project take if I add 2 people? I had to include some Dilbert cartoons when I'm talking about management. Well, it'll take 1 month for training to bring them up to speed on this system and how it all works, an extra month for the complexity of having to deal with talking to 2 extra people the whole time, and an extra month just dealing with the fact that people suck. If a project is late, the worst possible thing you can do is throw more warm bodies at it, because it's going to take me 2 months to teach them enough about the system to be useful. And while I'm busy teaching them, I'm not useful because I'm teaching them instead of writing code or testing or whatever it is I'm doing. The degree to which this varies depends on how early you add people and if you can absorb the cost, and the number of swim lanes. If you've not heard that phrase before, swim lanes are the number of independent parts of the system that can be worked on without bumping into each other. Projects have a natural maximum number of developers on them that I would argue is number of swim lanes times like 1.05. So if you have 3 swim lanes, 3, maybe 4 people, so you have a bit of excess capacity. If you have 8 swim lanes, 9 people is about as many as you can put on it. More than that, they're going to bump into each other. You're wasting people just throwing them at it, and it's just going to slow everyone down with more coordination. Which means, for a given project, the amount of time it's going to take versus the number of people you have, there is a natural optimal point. If you put more people onto it than that, it will take longer than if you just had fewer people. This was Brooks' claim. Based on your chuckling, when I say, is this still true? We can empirically, in our own experience, say, yep, this is true. Of course, I don't have any internet access here. This is supposed to be a tweet. When I was putting the talk together, I was lamenting the fact that I had enough material here for 2 talks. And so someone helpfully suggested I get a second speaker on stage, and we can both talk at the same time and give both talks at once. Because that would totally work, right? Right. Do we know any projects that try to deal with a problem and management by throwing more people at it? By just getting as many warm bodies working on it as possible? Can you think of any? Oh dear. How many communication paths is that? A lot. So what can we learn from that? Second question. Why are estimates always wrong? Who has never had an estimate that was off? I thought so. Why? Well, there are a couple of reasons that Brooks talks about. The first is the idea of the programming system product. When you estimate something, if you're a developer, odds are you're estimating the proof of concept. You're estimating just the program to get something that works and does what it's supposed to do. And that can take a weekend, a week, some relatively small, manageable amount of time. But that doesn't make it useful. That doesn't make it an actual product. If you want to flesh something out to be an actual product, it means you need to generalize it, you need to put more effort into testing, you need to document it, you need to figure out the maintenance plan for it. There's a lot that goes into productizing a shell script. And Brooks estimates that that is 3 times as much work as building it initially. 3 times as much work to productize. You could also turn it into a programming system, which means something other code or other tools can build off of. Doing that requires building and defining formal interfaces. It requires integration work to plug it into other pieces and see where it breaks. Not if it breaks, where it breaks. And fix those to make it stable enough that others can build off of it. Brooks estimates this also takes 3 times as much work. Which means, if you want an actual programming systems product that is a robust programming tool that others can build off of, that is 9 times more effort than just building something first in the first place. 9 times the effort. He also notes, especially if you want to productize it, it means you need a substantial bank of test cases exploring the input range and probing its boundaries, which must be prepared, run, and recorded. Substantial bank of test cases. Automated testing was already a standard expectation in 1975. You have no excuse. If you are not doing automated testing, you are wrong. There is no exception to that statement. It was true in 1975. Yes, it's still true today, 40 years later. Note, this does not mean add tests after the fact. It means fixing the bugs takes time, and writing the tests will help you find them, or avoid them in the first place for the cost of writing the test in the first place. Second thing that makes estimates not work. How fast can you code? Just ask yourself the question, how much code can you produce at once? It's not an exact number. I don't care how good you are. It may be a different number for different people, but it doesn't matter how good you are, it's not an exact number. If you simply extrapolate from how long it takes you to write a small program to the time it takes you to write a large program, that doesn't work. Extrapolation of time of a 100-yard dash shows that a man can run a mile in under 3 minutes. As of this last week, the current best is 3 minutes, 43 seconds. And that is substantially better than it was in 75. It turns out, Brooks quotes a number of studies from the early 70s that found the amount of effort you need to put in is a factor of the number of instructions produced to the power of 1.5. Which means, in layman's terms, the more code you have to write, the slower it's going to be per line over the course of the whole program. Writing more code takes longer per line of code. So you get a graph like this. It's from one of the studies in particular. This is where, what you would expect to be linearly. This is what you actually see in practice. That the more code you write, the longer it takes to write. Why? You have more interaction points internally. Even if it is just one person programming, even if it is just you, it takes longer because there's more going on in the code. Everything you touch is going to potentially break more things. The amount you have to keep in your head at once to make sure you don't break anything expands. The limiting factor here is humans. This is also true when you increase the number of people on the project, or the number of interactions between people on the project. Another study run by Joel Aaron found that if you have a large project with very few interactions between people, then one person can churn out 10,000 instructions per year. If they've got some middle level of interactions, I'm skipping over definitions of few, some, and many here, they're only going to produce half as much code. If they have a lot of interaction between other people in the team, 1,500. Almost an order of magnitude less code produced per person because they have to spend time talking to and coordinating with other people. This was multiple studies that found this pattern. In this case, they defined large as 25 programmers and 30,000 instructions. Now, there's one saving grace here, is that all of these studies were conducted on people writing in assembly. And so when we say instructions, we do mean instructions, CPU instructions. Another study, though, that Brooks quotes, found that the same curve followed for people writing in PL1, which was a contemporary of C in the early 70s, a programming language that I'm told people still use, although I've never seen it. But there was a higher level language, more akin to what we're used to. It followed the same curve, but for the number of statements. But one statement in PL1, C, PHP, whatever, is a lot more powerful than one CPU instruction. Which means a more powerful and expressive language does let you be more efficient. You are a more efficient developer if you're working in a higher level language that lets you do more with less code. But you still are going to run into that same problem of the larger your code base, the more lines of code in your code base, the longer it is going to take you to write, even if you never talk to anyone. And the more people you have to talk to, the longer it's going to take you per line. So what do you think? Is this still true? My experience says yes. Yep, this is still true. Of course, we just said very large programs were considered 25 people and 30,000 instructions. I think some of you see where this is going. Pop quiz, how many lines of code are in Drupal 8? This stat is actually as of one of the late betas, not even up to date yet. 237,000. That's without composer dependencies. So what can we learn from that? Next point. Planning and documentation. This matters. These go together. These are the same thing. You should be doing upfront documentation. Why? Because only when one writes do the gaps appear and inconsistencies protrude. The act of writing turns out to require hundreds of mini decisions. Those mini decisions matter. You need to make those. The act of trying to explain it to a document susses out all of these possible problems. It's like rubber ducking with your word processor. That's what upfront architecture is. It's not necessarily big upfront design and be done. It's a rubber ducking process. It is a design process. I worked on dozens of projects while I was at Palantir, and the ones that went smoothest were the ones where we had a clear plan from the beginning that we had written down and figured out the 50 other questions we need to ask the client before we start doing anything. If you start working before you figure out those 50 questions, it's going to be a lot harder to address those questions when they come up. Of course, the manual and written specification is a necessary tool, but not a sufficient one. You can have a formal definition of something, which is nice and precise, but not very readable. And what's missing is the why. How do things fit together? Why are they done this way? The code itself, no matter how self-documenting it is not going to answer that question. You need to have this documentation and keep it up to date. If you make a code change and you do not update the doc block, the code is not done. If you make a code change and don't update the architecture documentation, the code is not done. You're committing half-completed work if you aren't updating the documentation along the way. I ran into this when I joined platform.sh earlier this year. It's a startup, which means that they spent their first few years trying to make things work and get it working and not documenting the big picture. So I come in, I'm a director-level person, I am totally lost in how the thing works, or what repository is where, because it hasn't been documented. I've been doing a lot of work to fix that internally. As I learn things, I'm writing them down, I'm forcing other people to write docs. We're in the middle of a big overhaul of our public documentation. The documentation matters when you bring on new people, or just you remembering what you were thinking a month ago, because my memory is terrible. Brooks argues very strongly for top-down design. Top-down design means you architect the system first. Then you can, once you have that top-level big picture, you refine it and break it up into modules and break it up into pieces and plan each of those. Keep doing that until you figure out what your pieces are and how they're going to fit together. And they'll all be cohesive. Then you implement each module individually, test them separately, because that's going to catch more bugs that way. And this process should inform back up the architecture, up to and including, oh, well, I have to throw it away now because I totally got it wrong. This is divide and conquer, which is, if you learn nothing else about software architecture, divide and conquer is the key to building anything in software. Brooks also suggests you should just plan to throw away your first version. You're going to one way or another, so just build that into your plan. Because you don't know exactly what you need until you've actually built it and realize you did it wrong. It also means your version 1 is probably going to suck. Pretty much guaranteed, because you don't know what you're building until you've built it. See also anything Microsoft ships. As the running joke goes, it's never good until version 3. It's not unique to Microsoft. Of course, I'm sure some people in here at this point are now going, waterfall! Don't do waterfall, we know this, right? Waterfall evil. Well, Brooks actually said the same thing in the updated version 95. And he said, you know what, that is waterfall. That's a bad idea. You should still do top-down design, though, but do it iteratively. Start with an end-to-end big-picture skeleton that does nothing but compiles. Always have a runnable system that doesn't actually do anything, but has places in it to do things that are just stubbed out with dummy code that does nothing. You have a whole bunch of null implementations sitting around. And then you can grow modules into place, not plan them up front. You have your big picture, and then you grow pieces into them, and those pieces can evolve then independently of each other. It means you can rewrite or completely throw away individual modules independently of each other, or toss the whole baseline architecture and put those pieces into a new architecture. This is refactoring. Who's heard the term refactoring before? Refactoring is the process of throwing away your first version a little bit at a time. Plan for this. Build it into your schedule. It's going to happen one way or another if you don't want to ship crap. Plan for it. This approach necessitates top-down design, however, because it is a top-down growing of the software. You let the software grow organically top-down rather than sideways. It's bonsai here. Also, common sense, if not common practice, dictates that one should begin system debugging only after the pieces work. A couple of people are chuckling kind of nervously here. Yeah, you don't try to put everything together first. You unit test the individual pieces and make sure those work. Then you put them together and figure out where they don't fit. Architect top-down, design bottom-up. The same people that were complaining about waterfall a moment ago are probably now going, hey, look, Agile, right? Wrong. Who's seen this picture before describing Agile? This thing is terrible. For the love of God, don't think this is how software works. Have you ever tried to evolve a scooter into a bicycle? Have you ever tried to build a car out of a motorcycle? It doesn't work. You throw it away and start over. You're throwing it away twice in this model, not just once. This is a complete and total waste of time. If you're trying to get to here, why would you build something useless? Instead, you start with a skeleton that supports your end goal. It has 4 wheels. It has a base. It has enough weight to support doors. Then you iterate and add more pieces. And then you can say, oh, I want to change this piece, but I can still keep that baseline. Or, oh, now that I've got this, I know I can change it and add a different color and change the wheels, but they still got the skeleton, the chairs are all the same. All on that same basic skeleton. We started off building a car, we're still building a car, we can replace the doors along the way, but it's never going to turn into a jet engine. If we need to turn this into an airplane, we start over. So you don't plan to start over that much. This is the way you do an MVP. It also means you need decoupled components so that you can replace the tires without having to replace the doors. It also means you are not building the most client-important feature first. You are not building the most client-important feature first. You're building the baseline framework first, on which you can then hang the client-important features. Until you build wheels, it doesn't matter what the rest of the car looks like. The most important thing for the client may be that the car is green, but until there's wheels, they don't have a car. What do you think? Still true? Brooks right on this one? I'm going to say half right. He had to revise it, but 20 years later after the revision, yeah, this is true. It certainly reflects my experience over the last 15 years as a developer. In 1986, Brooks gave a presentation at a conference, which he later turned into an article, which then turned into a chapter in the new edition, called No Silver Bullet. No Silver Bullet talks about how there's a difference between the essential complexity of something and its accidental complexity. Incidental is probably the more colloquial term. Accidental is the philosophical term. The essential complexity are things where this is hard because the problem space is hard. This is going to be a lot of work because there's a lot of work involved. You can't simplify that. Incidental complexity or accidental complexity are things that are not part of the problem space. They're just work you have to do around it because the tools are hard to use. And Brooks argues in 1986 that the hard part of building software is the specification, design, and testing of the conceptual construct, not the labor of actually representing it. Bear in mind, in the 60s when he started working on IBM System 360, you execute your program by taking a stack of punch cards and walking down the hall to the elevator to go to the next floor down where the computer is. You wait in line, run your program by running through a stack. And you debug by the computer barking at you, and you take your stack of punch cards and walk back over to the elevator, back upstairs, back to your office, and stare at the punch cards until you figure out what's wrong. We've gotten a lot better than that. That walking time is accidental complexity. By the mid-'80s, Brooks argued, there is no single development which by itself promises even one order of magnitude improvement in productivity. Giving people their own computer was an order of magnitude improvement. Real-time debuggers, order of magnitude improvements. Higher level languages, so you're not writing assembly, order of magnitude improvements. We've run out of those. Most of the time spent on software these days is actually time spent on software, not just finding your tools, unless you don't know how to quit Vim. There is certainly room for improvement, but not to the degree that they saw in the 60s and 70s. So how do we attack the essential complexity of the system? How can we make ourselves more efficient if eliminating irrelevancies is a solved problem for the most part? Brooks lays out 3 or 4 alternatives that he recommends. One is rapid prototyping and organic growth of the system based on user feedback. We just talked about this one, iterative design. Buy versus build, and just mentor better architects. The most radical possible solution for constructing software is not to construct it at all. 1986. When Brooks started work in the 60s, software, people were happy to custom write every piece of software they used. Why? Well, if you're spending $20 million on a piece of hardware, spending $50,000 on custom software is a rounding error in your budget. It's not an extra cost center. I can get a fully functional computer for $10. I'm not spending $50,000 to custom develop software for it. Even in the 80s, people were buying stuff off the shelf. Why would you write your own spreadsheet when there's one you can just buy for $20? Why would you write your own web server when there's free ones available online? Reuse your software tools and reuse your components so you don't have to write them a second time. And that attacks the essence of programming. You solve it once and move on and just keep reusing it and spread the cost of that out over all the use cases. Now, he didn't use the phrase because it didn't exist at the time, but we just described open source. That is the essence of open source. Build it once, share it, don't build it again. Incrementally improve it, but you spread out the cost of development over a whole lot of users. The way to be more productive in writing code is to write less of it. It's to write less code. The way to be more productive is to reuse more code, which means sharing more code. Open source, that is what we do. Open source, I would argue, is the greatest productivity improvement in computer technology in the last 30 years. Also bear in mind, you need to grow great designers, because software construction is a creative process. It is much more like graphic design than it is engineering. Software is an intellectual exercise. I was actually just reading an article on the plane on the way here that said neurologists are running MRI scans of people developing, who are good developers, and they're not using the mathematical parts of their brains. Expert developers are not using the mathematical centers. They're using the language centers. They're using the same parts of the brain you use to learn a foreign language. That's where in the brain this works. It is a creative linguistic process. And study after study shows that the best designers produce structures that are faster, smaller, simpler, cleaner, and produced with less effort. Design matters. I'm using the word design here deliberately. It is more like graphic design than it is like engineering. Architecting the system is not a coding skill. It is a design skill. And that it is a separate skill set from development. And that means it needs the recognition that goes along with that. Whether that means salary, position, authority, it is not junior to management. A really good designer, their position in your corporate hierarchy, Brooks argues, should be equivalent to senior management because they are that important to your process. They are that important to your output. We need better mentoring. He's saying this in 1975. Better mentoring. Actually, this is in 86, but he talked about it in 75 too. Identify candidates early. They may not be the most experienced developers because architecture and development are different skill sets. Give them a career mentor. Actively pair them up with somebody who can train them. Apprenticeships. Give them extra education. Let them do solo work where they get to architect things. Encourage collaboration with others who are in the same position, who are also working as designers. All of these are things the design world does. These are things that the software architecture world needs to do. We need to model more on the design world than on the development world. What do you think? Get this one right?
Yes.
Yeah. Open source, totally. Mentoring, totally. Neurology is saying he was right about it being a design skill. And finally, what Brooks argues, and I would agree, is the most important point in the entire book, that he spreads over several chapters, which is the idea of conceptual integrity. The conceptual integrity of the product, as perceived by the user, is the single most important factor in ease of use. You want your users to have one mental model, one way of thinking about the system, one set of patterns they need to memorize. They're going to have to memorize something, but you want to give them one vision of the system. Ease of use is not a simple number. It is a ratio. It is the amount of functionality you get for a given complexity. Neither function nor functionality alone or simplicity alone define good. A good design is one that has a really high ratio here. Picture 3D Studio Max or Adobe Photoshop. These are hard to learn. They are very complex tools because they are complex tools. The problem space is hard. But you get a ton of functionality out of them. Compare that with a text editor, which has very low functionality and also very low complexity. By text editor here, I don't mean Emacs. I made fun of VI earlier. I have to make fun of Emacs now, just to be fair. But less functionality, but also low complexity. So they're just as easy to use. Yes, I just said a text editor is just as easy to use as Photoshop because they're at a different their ratio can be similar. Simplicity and straightforwardness proceed from conceptual integrity. Conceptual integrity, therefore, is the most important consideration in system design. It is better, Brooks argues, to have a consistent design with fewer features if those features break the conceptual integrity. You get a better product with conceptual integrity than you do with functionality. Also, conceptual integrity of the product not only makes it easier to use, it makes it easier to build and less subject to bugs. If there's only one mental model, one set of patterns to think about, that applies not just to end users, but to the developers building it. If I have to think of one set of patterns, I know, oh, I see this thing, I recognize how it works. The same pattern I can apply in a whole bunch of places that makes it easier for me to construct. And if I know how to construct it more easily, if it's consistent, I'm less likely to have a mismatch between assumptions in different places, which are the source of so many bugs. So how do we get that? How do we get a good conceptual integrity? Brooks argues a smart division of labor. Two ways you can do that. One is what he calls a surgical team, where you have one person whose job is nothing but design and build. Design and build and nothing else. And then you have a constellation of people around them, just like a surgeon has a team around them, who are no less important than the surgeon, whose job is to do everything else so that the surgeon is not distracted from the fact that he has a knife hovering under your aorta. You have document people, you have testers, you have QA, you have client coordination, you have a whole bunch of other people who are doing everything else so that the person or small people building it can just do that and not get distracted. And then you get conceptual integrity. Honestly, that rarely happens. What is more likely to happen is Brooks's alternate proposal, which is the design must proceed from one mind or a very small number of agreeing minds. That you split off the architecture and the implementation into different people. That does not mean, if you have a small number of minds, that you have monothink. You don't want them completely in agreement on everything. But they should all be pretty much on the same page with the same vision for what the system looks like. Same conceptual picture in their mind, so that they can all be targeting that same vision at the same time. If they're fighting on that, you'll end up with two systems overlapping each other. The architect is the user's agent. It is their job to bring professional and technical knowledge to bear in the unalloyed interest of the user, as opposed to the salesman, the fraudgator, whoever. They are the user advocate. They are designing the system for the end user who will be using it, which in the case of a programming system could be another developer. But they are still designing something for the end user. And someone is going to cry that this is cathedral design. We're open source, cathedral and the bazaar, bazaar style of model. This is an aristocracy. Too bad. Cathedrals stand for hundreds of years, and they are consistent. You walk into a cathedral, you know how it's laid out. System 360, the code from it still runs 50 years later. What open source projects can claim the same? Very, very few. Design is a top-down process. The fact that we're in software doesn't change that. If you are dealing with Apple, design flows down from Johnny Ives. There are a lot of other people involved, a lot of incredibly smart people, but Johnny Ives is calling the shots. Matthias Duarte is the designer at Google, and everything flows down from that consistent conceptual vision. Any Unix, the design for Unix was set down in the early 70s and has not changed. It came from 2 people. And it still works. It's still a good architecture. HTTP, it was designed up front by a small number of people. You can implement it in a browser however you want, but that spec is that spec, and that design works. That is our entire industry built on that, designed by a small number of people. The wisdom of the crowds isn't when it comes to design. That doesn't mean that the implementer is lesser. They are peers. The architect designs the watch dial and the hands. The implementer figures out what bells and gears and whistles will get there, which could be different for a wristwatch versus Big Ben in London. But the architecture is the same concept. Architecture is not a democratic process. Democratic architecture is called mud. The architect must always be prepared to show an implementation of a feature, but not dictate the implementation. What gets done is the architects to control. They should get feedback from and take input from the implementer, but they, at the end of the day, need to have that decisive authority to decide, this is what we're going to do. The implementer must have the final authority on, this is how we're going to do it. They are not, it's not a superior-inferior relationship. They are equals division of labor. This also reduces communication channels. Communication can flow through the architect. When someone makes a decision that affects architecture, they talk to the architect communicates to everyone else. That lets your team scale larger. You can divide and conquer and have layers of architects like Apple and Google do, like any large system needs to have. This is an ongoing cooperative effort with a high level of communication, but it's a structured communication, not big and ad hoc. That gives you a better system. Can we name any systems that have been designed over a long period of time, ad hoc, by a lot of different people just throwing stuff at it without a big, really good plan? Do we know any systems that were designed by lots of different people and so are internally very inconsistent and therefore hard to learn? Do we know any systems where there was a relatively small number of people who, through sheer force of stubborn will, ended up being the driving force behind the way it worked, and it's therefore better and more consistent and easier to learn according to everyone who's tried to do so? What can we learn from that? We're talking about big software here. How big is big? 25 people, 30 people, 3,000 people? After teaching a software engineering laboratory more than 20 times, I came to insist teams as small as 4 choose a manager and a separate architect. As small as 4. One person with architectural vision, one person coordinating, and 2 or more people actually building stuff. That completely is true according to my experience at Palantir. The best projects we had were the ones where someone was driving and someone was navigating. If you're making a movie, you have a director, you have a producer, and then you have your cast and crew. The same model applies. You need that division of process person, vision person, and implementers. That does not mean that there's a hierarchy between them. It does not mean one is more important than the other or necessarily needs to get paid more. But these are different roles. The architect needs to have that control. Either the manager or the architect could be the boss on the project, as long as someone is. So what can we learn from all of this? What can we learn from 40 years of ancient knowledge? First and foremost, software construction is a creative process. It is not engineering, it is design. Divide and conquer. This is the way to solve almost any problem in computer science or engineering or development. Break it down into smaller pieces, solve those pieces, break it back up. That includes your org chart. That includes your team. Build shareable programming systems products. That 9-time investment is worth it if you then use something 10 times. Because then you only had to do that work once. Open source is the #1 productivity improvement of the last 30 years. Decouple your libraries from your framework as much as possible. You can change them out more easily, you can redevelop them more easily, you can debug them more easily. This is a special case of divide and conquer. Do not couple your code to a particular framework or dependency injection container. Follow top-down design. Plan up front. Will the plan change over time? Absolutely. Of course it will. Keep the docs up to date. If you don't, you're not doing your job. And most of all, empower your architects to make decisions. Top-down design means top-down decisions. And the most successful projects in software history are top-down design, are designed on the product of one or a very small number of people, implemented by a large number. Crowdsourced architecture isn't an architecture. This is 40-year-old knowledge. And they come as a surprise to that people knew a thing or two in the 70s. This is strange to a lot of young programmers. Donald Knuth, the author of The Art of Computer Programming and the father of analysis of algorithms. He's right. What can we learn from this? Thank you.